geometric distribution, and we're going to consider this example in which a coin is going to be tossed until it lands heads. The probability for the coin to land heads is 0.3. We want to answer these questions. So what's the probability the coin needs to be tossed exactly 3 times to land heads? Uh, what's the probability it needs to be tossed more than 3 times? And what does the graph of the probability distribution look like? So let's answer this question. The first important thing to note is that this is a geometric distribution. The properties are satisfied. So for example, each toss is independent, meaning one toss does not affect another. That seems relatively intuitive, that the outcome of one coin should have no bearing on the next. The probability is the same each time you toss the coin. And finally, the random variable x here is the number of tosses until the coin lands heads. And that last part is fairly important to recognize. So if we want to calculate the probability the coin needs to be tossed exactly 3 times, we use the probability mass function. And that comes from the SciPy stats library, and we just do stats.geom with the probability mass function, and we count, and we see that it's about 14.5%, that it's exactly 3 times. Now I ask the question, what's the probability it takes more than 3 times? Now remember, in part A, we only calculate the probability of exactly 3 times, so it's not 1 minus 14.6%. It needs to be a little bit more involved than that, because remember, the coin could be tossed once, it could be tossed twice, or it could be 3 times. That would be the complement of the event. Okay? So if I subtract all 3 of those and I calculate all 3 of those probabilities, the probability of 1, the probability of 2, the probability of 3, that's the cumulative distribution function, the CDF. And I can do 1 minus that to get the greater than probability. And that winds up being 34%. Okay? So this seems to indicate it will land heads sooner rather than later. Like for example, there's only a 34% chance that it needs more than 3 tosses of the coin. So if I look at a graph of the probabilities, the most common outcome is that it just takes 1 toss, then 2 tosses, then 3 tosses, and it goes down in probability quite rapidly. Okay. If I change the probability to be 50%, let's see what happens to the graph. It becomes even more likely then that it takes fewer tosses of the coin, because for example, on the first toss I have a 50% chance of getting the heads right away. So these probabilities increase. That first one is 50%, the second one goes down dramatically. And so it's more likely for it to occur with less tosses of the coin. If I change the probability to be something really small, like only 5%, it'll take more tosses of the coin, and that's what this graph shows here. It has that same general trend of getting less and less likely that it takes more tosses, but now the tosses later on are still quite likely relative to the ones early on. Okay, so this is the graph of the geometric distributions, and this is how we solve these problems. Thank you.